Smart adhesives with switchable adhesion are considered important materials in medical and smart printing systems. Now, in relation to this, scientists have explored the use of several biological adhesive systems inspired from nature, such as gecko's foot or feet of frogs, observing how they adhere to surfaces and then applying the same mechanisms to their own adhesives. One novel discovery makes use of the octopus suckers or tentacles' excellent switchable wet adhesion capability. As you can see, you have here a cavity and three other muscles. The contraction of radial and meridional muscles increase the volume of a cavity, causing pressure decrease inside, resulting to adhesion. On the other hand, when the circular muscles contract, the pressure in and out of the cavity becomes the same, detaching the sucker from the surface. Using this, Ko and his group from Korea Institute of Science and Technology created an adhesive of the same adhesion mechanism, and this time it's temperature controlled. The material is composed of a PDMS or polydimethylsiloxane film coated with PNEPAM or poly-N-isopropyl acrylamide hydrogel as the actuator. PNEPAM particularly has an inverse solubility upon heating, which means that its hydrophilicity changes depending on the temperature. At temperatures lower than 32 degrees Celsius, water molecules surround and form hydrogen bonds with the polymer. The negative enthalpy of hydrogen bonding dominates and PNEPAM is dissolved in the solution. At temperatures higher than 32 degrees Celsius, the negative entropy of mixing dominates, causing the polymer to release water molecules. PNEPAM instead H-bonds with adjacent groups to create a phase separate from water. Following that mechanism, PNEPAM coating on the adhesive itself becomes hydrophobic and shrinks at higher temperature, creating a larger cavity. The pressure difference allows easy adhesion, and at lower temperature, on the other hand, PNEPAM becomes hydrophilic and swells, decreasing the pressure difference and the adhesive strength. Based on their study, the adhesive strength spikes from 0.32 kilopascals to 94 kilopascals at high temperature. Compared to normal adhesives, the smart adhesive pad showed better adhesion. The on and off adhesion could be repeated just by changing the temperature for up to 100 times. To prove the concept, they transfer printed indium gallium arsenide nanomembranes on a silicon dioxide substrate. As a result, they were able to transfer 100% of the material without causing surface damage, not only on the silicon dioxide substrate, but also on heterogeneous surfaces such as polyimide and PET. More importantly, the transistor was working excellently with high electron mobility and high on or off current ratio. So far, the discovery has not been patented yet. However, several patents for adhesives have been published. These use polymer fibers applying adhesion mechanisms of other biological systems, but different process of adhesion. Lastly, the material can further be used to create high-performance transistors and optoelectronic devices. It can also be used to create medical adhesives for easy surgeries that require intricate details, as well as heat-sensitive medical adhesives like, for example, Band-Aids.